Hi, welcome to this featured training on modeling, analyzing, and designing of PEB structure in STAT and RAM connection. So my name is Bishwatosh Purkayastha, and I'm here as a senior structural engineer in Bentley Systems, empowering our user to work smarter with our structural product from the family of STAT and RAM. So today I will walk you through the brief overview and the workflow on the effective way of structural modeling, analyzing, and designing of pre-engineered building. So let's get started. So the products that we are taking for this entire modeling is basically STAT Connect Edition and then some portion of the connection designed by RAM connection software. We will basically model, apply the load, assign various support condition, then various sectional property, analyze them, and then perform the member design in StatPro. And then we'll take to export few of the connections to RAM connection and then design them. Okay, now let's compare the pre-engineered building, that is the PEB, with the conventional steel buildings. Now, this is very important. Need to first understand the basic difference and its structural arrangement in both the systems. Now, the normal building or the conventional building is quite popular and it has been used for various products, for various projects, and for various utility purpose. Now, for the conventional steel building, the structural members that are used are mostly rolled, that is the hot rolled sections, and the materials that are produced or manufactured are in the plants with some standard shapes. So these are not basically the custom shapes; these are some standard shapes, and the raw material are processed in the site for the desired form and then erected. Now, the modification here can be done during the erection by cutting, welding to give it various shapes and to put it in various orientation, various arrangement. Uh, Here, the truss systems are the most conventional system in this conventional steel building. Now, if we compare it with the pre-engineered building, that is the PEB building, here, the building approach is much more smarter. Here, the structural members are basically manufactured or produced in the plant itself. So, basically, it's not like hot rolled. It's like some components are taken or being carved out from the plate elements and they are welded together as per the requirement. And the manufacture of the structural member is done as per the customer's choice and need. So here the optimization can be very much possible because you can control the shapes and its sizes. So these components are made in modular or completely in knocked condition for transportation because these are mostly being transported as a dismantled or in a modular form and then in the yard or in the site where the construction is in progress, these are being dumped and then as part of the drawing, they are being assembled and then erected. Now here the welding, cutting and other kind of process are not performed at the customer site because it's already been welded or its shapes has already been made in the steel yard from where it has been transported back to the site. So here you just need to assemble them. So basically the assembly on the site is done by the bolted connections. And if some very rare situation, you might have to weld, but mostly for the assembly, they are bolted. And next is why the pre-engineered building, why we are talking of this pre-engineered building that is a PEB. Now we need to understand what is the reason that this kind of building system are so popular. Now there are several reasons, several advantages over the conventional building, but the most important advantages has been listed out here. The first one is the reduction in the construction time. Now, when we are doing this construction of this pre-engineered building, Normally, these are fabricated in the factory and they are transported in a modular form back to the site, construction site, where they are assembled and then erected. Now, in the factory, they have a well setup, like machines, they have some process, they have some separate dedicated team. They are following all those regular process of fabrication. And that's the reason in the factory, these are fabricated much more faster compared to some conventional building where the most of the fabrication parts are done in the yard. So from the construction time, it is much more reduced compared to the regular building system. And then also the cost factor. The cost is much more lower compared to the conventional building. The reason is it's like, in the factory, they have some well set up. So just like copy and paste, somewhat like this, they have some system, they have some machines, they have some dedicated team, and that's the reason there is a lot of involvement of different kind of technologies and machines, and that's the reason the labor cost is much more lower compared to the conventional building. And then we always have the flexibility to expand the building system. Now, in different kinds of utility projects, in different kinds of industry, over the time they want to expand that building because of some business expansion. Now, in this pre-engineered building system, as these are being carried as a modular system, and then these are being assembled. So basically, this is just like a portable system where you can again dismantle and carry it back to some other site. So you always have some flexibility to augment the existing building and expand them. And then the quality control. Now, that is a very important part here. The quality control is a very key reason for this pre-engineered building because everything is done. Most of the important, the structural integration of fabrication is being done in the factory. Now, again, I'm reiterating that in the factory, everything is well organized. There is a certain process that are maintained. So certain teams are there. Some quality control team is there. Some machines are involved in all those cutting and then fabricating, welding and all. So as this is much more organized, so the quality control can be well established in the factory rather than the yard. Then the low maintenance. Now, one of the example for this low maintenance is the painting. Now, most of the steel structure should be well coated by some film so that they should be corrosion resistant, so that they have a good life over the time, and they should be long lasting as well. Now, in the factory, they have some modern facility where they are coating it, primering it, painting it by some advanced process, guaranteeing you the better coating compared to the process that are being practiced in the conventional building in the construction site. Then this kind of pre-engineered building are having a lot of flexibility, and one can have some energy efficient roofing and wall system as well, mostly for a very hot climate, just like in Gulf or some other areas where there is a extremely high temperature. They can have some specialized system for like energy efficient roof and wall system. Then there is always something called architectural flexibility. Now, as you know that in different kinds of building shapes or its geometry, due to some utility reason and due to some architectural reason, there are different kinds of challenging shapes. Now, in the conventional system, we have to work out with the available hot roll sections, and sometimes this is not possible to give some desired shapes. Just like, for example, there is a curved like shape, and its depth of the section is uniformly varying, or maybe varying as a function of its length. So these kind of shapes are not possible in the hot roll because it's a standard shapes. As opposed to that, in the pre-engineered building, as these components like flange and web, these are mostly carved out from single plate elements. So they will see the drawing, and as per the drawing, they will figure out the shape, and they have a very good facility. They have the advanced CNC machine where they will just carve out the desired shapes as per the architectural requirements. Now, the PB structures are widely used in several industrial, commercial, as well as other utility structures, right from airport terminals, industrial buildings, enclosure, factory, cold storage building, then railway station, metro station, then warehouse, bridges, you just name it. And even nowadays, contractors are using the PB method for several residential structures. So over the time, this method is booming for several advantages that we had discussed a while ago. So it is very important to understand the proper way of modeling, analyzing, and designing various key components of PB structures with our products. Okay, now let's open a STAD model, or rather, let's create a new STAD model. Now I'm using the STAD Pro Connect edition, and please be noted that all of you are advised to use the Connect edition. There are several reasons that for using the Connect edition. First of all, we have different interfaces, different tools, and different options to adjust different nitty-gritties related to the modeling. Now, here you can see once I launch StatPro, you can see this introduction page or the startup page where you have three different options like the type like analytical, physical, and building. Now, in the analytical modeler, basically it's the same view or it's the same interface that we have been seeing it for a long time now, the common StatPro view. But the new one is the physical modeler and the building. Forget about the building modeler because it's more to do with the typical building where we have the slab and floor plans, and we are doing it by the building planner. But today we are on focus to the building. We'll focus to the combination of analytical and physical modeler. So today we are going to model a simple warehouse type building or some industrial structure which is having some sloped roof, and conventionally what is used is like either the conventional steel building or the pre-engineered building where we have seen something like tapering of the member. We call it the web tapered member. So, what's the difference between the analytical and physical modeler? That's a very important thing to understand, and we will just understand why it is important in this kind of structure to model and how it is going to help your modeling and other operation workflow. Now, the physical modeler is something like the interface that will give an option to define the inputs of the structure as how we see in it our physical sense. And the analytical member is something different. It's like how program sees those structure from its own standpoint or its own requirement. Now to simplify this, it's like, for example, take a slab and it's being connected with a lot of columns and beams. Now in our physical sense, we don't see any kind of meshing, any kind of nodes thus created. So don't have to deal with that. What we see is a simple continuous slab, a single block, and the members or the columns, even the members or the beams are continuous beam. We don't see any joints like nodes. We see a continuity of the beams or the members. Now, why do we need those joints and those mesh? This is just to discretize your model to create more nodes where the response of the structure would be calculated by solving the different equations involved in the finite element modeling. So basically, we are discretizing it. So, but if you want to model those discretized representation is very much challenging sometimes. For example, you need to maintain some parameters like the meshing should be proper, it should maintain the good aspect ratio, then there should be a well-defined shape, then connectivity should be proper, On top of that, if you want to make any changes, like if you have already meshed the plate and there is an opening and you want to shift the opening in the regular or the conventional approach instead, then it's a very difficult task. Now here the physical modeler is going to help us. The physical modeler, we are not going to model the meshing and all those things. We are modeling the physical solid elements like slab or beam. All those internal meshing nodes and everything would be regenerated by the program. And it also gives an option to adjust the model over the time. If there is any revision in the model, for example, you want to shift the location of the opening or location of the column which is connected to the slab, you can easily do that without deleting the meshing. Now you are defining the information in the physical sense, and program is creating the analytical modeler at the backdrop, and it is done automatically by the program. So today we will create the web tapered member in the physical modeler, and you will see how one can easily model them and how they can adjust all those alignments. Okay, now let's give a name to the file and select the physical, and you can also adjust some other parameters like license, configuration, and also the unit system. So we are selecting the matrix, create the new model. You can see this is a new interface, and this is the interface of the physical modeler. Now here you can choose the grid. The grid system is more or less same as the analytical modeler, where you can define the spacing and number of repetition of those spacings. And the global axis system is same. The y is represented as the vertical direction, that is the gravity direction. Here you'll get some added features like you can add multiple UCS. UCS is nothing but the global access system. You can create multiple UCS as a reference, and that would facilitate the user to refine his modeling and to model it much more efficiently compared to the normal scenario. Okay, now here we are maintaining a spacing of say 1 meter, and we are defining the repetitions on one axis as 20 and on this lateral axis as 10. Now this is a very simple grid layout, and it's elevation. Now we'll model one of the base of my pre-engineered building structure. You can see I have selected like this, maintain a height of say 1, 2, 3, 4, 5, I think 5 meter. Now you can just simply you can drag the cursor and you can model it accordingly. This is the slope beams. Now here you can see it's a very simple representation. Now in the physical modeler you also have the choice to assign different section profile. Just like in the conventional way, you have two different methods of selection. One is directly from the section database, and one is you can create your own custom shape, what you call it, the prismatic or the general shape, and you can assign it. Now here what we'll do is, say for example in this one, it is the basically the I-shape section whose web depth is being changed over the length. So basically it's a web tapered I-shaped section. So the fundamentally it is a I-shaped section. So first of all we need to select the profile as I. So give some information of its thickness of the flange and web, the width of the flange. Regarding the depth, you just keep it same. We will change the initial and the final depth later on, but other parameters like thickness of the flange, thickness of the web, the width of the flange, and all those things you need to define it here. So once you are done, let's assign it. Now you can see this is basically a uniformed depth I-shape section. You can see here depth is not varying. Now from here we will choose some option by which we can change the depth across its length. Now go to member, and there is a new option we have added in the recent version of Connect Edition called Assign Taper. Now this is the default depth that we have maintained like 0.25. Now from here you can change the depth at the start or the end. Now how to define the start, how to know the start and the end is just like the starting node and the end node of the beam. You can see it in the table on the right side that is shown in the screen. Okay, now this is the 3D view. Now you can see that we have defined the different depth at the start and the end nodes. Now, as the orientation of the start and end nodes are being modeled in this elevation, it has accordingly rendered its shape. Now you can see the left side looks quite realistic, but the right side is something like it's quite absurd. So the right side should have been the mirror image of the left hand portion. So what we can do is we can switch the incidence or switch or swap the start nodes and the end nodes. The same as in the analytical modeler, we have the feature called switch incidence. Now, in the physical modeler also, we have the similar option. Go to the member, and there is a tool called exchange connectivity. It's the same thing as a switch incidence. Now, the moment you click on this, it will swap the incidence. Now you can see this representation of this bay looks quite realistic, but there is some fine adjustment needed. And for this, we are here in the physical modeler where we have got some added choice to fine tune this alignment. Now you can see at the junction there is a gap where those slope beam is meeting the column, and also these columns are straight. In the real life scenario, for the pre-engineered building, the outer face is generally straight, but the inner face is inclined. Basically, we have maintained like the center line or the shear center of the column is straight, and all the external and internal face of that column are inclined. That should not be the actual representation of the structure. So we need to adjust this alignment. Instead, we have this, especially in the physical modeler, we have this option. If you would have done it conventionally, you could have done by using the offset command. For every member, you have to calculate the distance that is required to shift the nodes. And that's a very painful task. For each and every nodes, you have to calculate the distance, considering that these are sloped. So it's a very Herculean task to do that. But in the Connect edition physical modeler, the latest one, we have the option by which you can choose that, okay, you want to flash it with respect to the outer flange of that I-shape section, or you want to maintain the connectivity across its centroid or the inner face. You have the choice here. So let's see how to do that. Now, before we adjust the alignment, just to let you know that this is a pre-engineered building where we have to also model the lateral members like purlins, the girts, the bracings and all. Now for defining the lateral members like purlins or girts, we need to also define the location where they will be meeting this base. So basically we will create some nodes as a reference where those lateral members should be connected. So you can split the member, or you can without splitting the member, or you can create the nodes. Now, in the physical modeler, we have option to adjust any kind of inputs from the spreadsheet or the table you can see. Just like in normal Stat Pro, that is an analytical modeler, you can see a table always on the right side to adjust the values and different kinds of inputs. If you think that, okay, this is the input which is not supposed to be there, it should be adjusted, you can go to that right side table and you can modify the values. Same thing we have it here, we call it the spreadsheet. So we can also create the node at any intermediate points, either by splitting, selecting the member and use the split option, and also you can go to the table and you define the coordinate where the node is supposed to be located. Now, by this approach, I have split the tapered member to create some internal nodes, and also I have introduced few nodes at the columns. Now you can see the nodes are not that visible in the screen. If you just zoom in, you can see some dots at the intermediate portion. Now, the moment you click or select the member, you can always see a new dialog box that would be popped up called member. And there you can see you have the choice to select the exact location of the connectivity between the different two connected members. By default, the connection is always being considered at the shear center, or for this case, it is centroid because in this kind of symmetric section, shear center and the centroid are coinciding with each other. But if you think that, okay, my connectivity should be flashed at the external face of the flange, then you need to select like top, bottom, left, or right. You can just play around and you can understand that, okay, how they are behaving. Now, for example, if I select this column and use any option from this adjustment, this one. So if you select like any of the option randomly, for example, here if I select top left, so it is going on the other side because we are viewing it from the opposite end. So by this way, you can just play around and see which option is better suiting this kind of arrangement. Now we have some different options like bottom center, right center, geometric centroid, and so on. Basically, this is off doing the offset. Now, in the regular offset, you have to calculate that you have to know the dimension of that offset distance and then assign. But here you didn't have to. You just define that, okay, this is the reference point along which the connectivity is to be established. Now, please note that this kind of offsetting the member nodes can be done with respect to the global access system or also with respect to the local access system. So just check which option is best suited for your modeling. In my case, I have tried a few of them as a global and rest of them as local, and it works best for me. I have just played around and just chose the bottom right, top right, and just experience that, okay, this is the option which is best suiting this kind of arrangement. And I have modeled further with this kind of selections. So after selecting different options, I could finally figure out the final alignment and the representation. Now it looks quite realistic how it should be in the real life scenario. You can see the external faces of the tapered wave are flashed and also the internal one. So there is no gap in between, and also you can see the external face is perfectly vertical and the internal part is having the slope. So this is how the alignment and this is how the geometry of the tapered PEB section should be. Now, if you want to see that how the local axes are being oriented, in which direction they are pointing, you can also switch on the local axis orientation tab. So I have selected or adjust the alignment mostly with reference to the local axis system. Now that my modeling and the fine adjustment of one of the base is almost over, I can clone them laterally so that I can give a three-dimensional impression to generate the entire building. So for this, we can use something called translational repeat. This is same as the translational repeat, which we have been seeing for a long time in the conventional way of modeling in the analytical modeler. The same thing is here. You just need to define the spacing and the direction where it is supposed to perform the repetition. So I have maintained a distance of around 5 meter, and once you have done it, you can see that if in the 3D view, all of them has been repeated, and it looks like a three-dimensional building, and it looks more realistic, like a building structure, that is the factory shed. And you can see some red lines. These are the connectors joining each of those parallel bays because we have selected like option called link. We need to assign some property to those red lines. Basically, these would be representing the purlins or the girds. Also, you can add them manually. If you do not want that all the members should be linked at all the nodes, generating the links, you can select like, okay, my central apex portion should be linked by the members, and rest of them I can add them manually. Then you can do that. So in this one, you can see some option called snap to grid and snap to node. This is very important to meticulously select any particular node or the grid. So I will connect them laterally to represent the purlins. Similar way, I can connect the joints on its wall to represent the girds. Now here you please note that we are going to assign the property to those girds and the purlins. We have only assigned the geometric attributes to the web tapered members, but these purlins and girds, which are acting as a connector, they are having the missing property. So we need to assign some information like its material property and its geometrical shape. Now, generally in the pre-engineered building, these purlins or the girds are taken as the cold form section. Also, you have the choice to use the hot roll, but in this model, we will choose the cold form sections. So, in this Stat Pro Connect edition, we have a very decent library to choose the cold form section. So, for example, here we can go to the section and from the catalog, if you go to the standard hot roll, you can see the cold form sections. I have chosen I can choose either Indian or the US, and you can see there are different options because we have included the entire library as defined by the code. So these are some of the standard cold form sections. So here I will choose the Z-shaped cold form section and also the C-shaped cold form section. Mostly for the girts, I will select the C-shape, and for the roofing, we will use the Z-shaped cold form sections. Now you can see in this picture, um, these lines are passing through the center of those beams and columns. Basically, we have adjusted the connection between the beams and columns, but all those lateral members, that is the purlins or grid lines, we haven't yet adjusted. We have only used the adjustment with the offset to those beams and columns. But if you just imagine the realistic scenario, these members or this cold form sections should not pass through the center. That these members should be connected at some face. For example, on the roofing, they should rest on the top flange of the tapered member, and for the girts also, it should be attached to the external face of the tapered column. So here we will use the same feature, that is the position. We will adjust the position of the section. So first let's assign, and then we would adjust its position. So I have selected some of the standard shapes. Might not be that look very realistic, but roughly they looks quite decent. So you can use your own shape. So I have assigned to one of the girds. Now you can see some thickness being represented in this rendered view. Now we'll assign the col form section specification to all the parallel purlins. First select them, going to the catalog, and similar way we will choose the right section that we need and assign them. So this time I will choose the Z with lips. I'm selecting some of the section which I think that they looks quite realistic. You can, as I mentioned, you can choose your own specification. So you can see this section has been assigned, so they looks quite thick. Now you can see the analytical modeler view if you click on analysis model, and if you want to see the three-dimensional view, now you can see. Now I have adjusted this position of those coalform section by the same way of repositioning them as and selected the reference line where they should be connected. And I have already done that, that these members should be sitting on the top of the tapered slope beams. So you can see that I have used here, like in the member 70, top option I have used, and it is just sitting on the top of that. If I zoom it, you can see it is perfectly sitting on the top flange of the tapered section. So that's the beauty of modeling with the physical modeler. You have the choice to exactly place the member um, to its connected element, and by default generally the connection is established through its shear center or the centroid, but here you can exactly realign and reposition them. Now once you are happy with the modeling, you can go back to the analytical modeler to just see how it looks like when the analytical modeler or the analytical model is created. So click on the analytical modeling, and it will take you to the regular view of StatPro. And you can see there is a window, small window that pops up where it is just creating several information. Basically, it is creating the analytical model. Now this is the normal stat view. Now you can see those beams and columns and purlins are exactly not facing at its center line. There is some offset. You can see if you just zoom in, you can see some offset. I haven't defined this offset command, and I haven't defined the value of that offset. I have just chosen the reference location where the two different connected members should be meeting together. Now, if you think that still a few of the members are not exactly being placed on the tapered member or any other connected members, then you need to go back to the physical modeler, because maybe that you haven't defined the exact position, and you can again readjust its location. Now, this placement of these girds or the purlins at its exact position, maybe it's connected to the tapered member at the centroid or at the top flange. That's not that much important, and the result is not that much significant. The response or the change in result is not that much significant, but sometimes a user might want to model exactly how it should be in the real life scenario, because if you model at the centroid, if there is any lateral load due to this lever arm, there won't be any net moment or a kind of couple would be generated. But if it is located or connected at some certain distance from the neutral axis, then due to this lever arm distance, certain amount of the torque or the moment would be generated. So for that reason, or for that very same structural behavior, we want to model it as it should be in the real life scenario. Or else you can go with the conventional way of modeling. So here it looks like I need to do some fine adjustment. Few of the um, cold form section is not exactly placed on the top flange of the tapered member. I can just play around and fine tune them by using this cross section position and choose the right reference line for the alignment. So I've just changed from global to local, and that has served my purpose. So I have just fine-tuned and just came back to the analytical modeler to see the rendered view. Now let's see if that makes any changes here. Now this time it looks better, and it is exactly been placed on the top flange. Previously, if you have noticed that it was somehow embedded inside the top flange, but right now it is perfectly being placed. Anyway, now from here on we will move forward to add some other modeling attributes. So same way I can reposition the girds. So looks like in the 3D view you can see here everything looks perfectly connected. There is no gap, and all the members which are supposed to be connected at the junction at the different phase, they are well flushed. Now this is a coliform Z-shaped section with the lips. So you can see here we have perfectly placed it at the extreme surface of the external flange of the tapered section. Same thing for the top. Now you can see here I'm quickly readjusting it with respect to the required axis system. And if you think that few of the members are having some missing property, like some steels are not assigned, some sectional informations are not assigned, only you can see some line diagram, then all you can do is you can directly go to select member and go to the missing attributes, then you can get them highlighted. And the easy way to assign is go to the spreadsheet, where you can just simply copy. Say, for example, if any of the member is already having the property of steel, you can copy that and paste it to the uh, members which have the property missing. So by this way, you can simply copy and drag the entire cells which has the missing property and simply paste it. So this is the quickest way you can assign the property which is apparently missing in this model. So I'm just giving the a final touch up to this model and just figuring out the missing properties, and accordingly I am just reassigning a few of the properties that are not assigned so that my model is complete as far as the structural and the material information is concerned. Now again, if I go back to the analytical model, you can see here I'm going back to the analytical model. Now let's 3D render it. Now you can see here from the rendering image itself, you can see that if there is any line element there, or if it looks like a solid well assigned section, so that you can identify like, okay, my sections are all assigned properly, there is no such missing property. Okay, now here it looks fine. You can see all those sections seems to have some thickness, some depth, and it's also manifest that properties are assigned. Now, if you go to this property table, you can see those taper sections are displayed. Now, these tapered sections are the part of the entire continuous system. You didn't have to worry like each of the analytical sections are having the individual starting and the end depth. No, it's a continuous section that we have assigned as a considering as a physical member in the physical modeler so that the slope is going to be uniform throughout the collinear member. So here let's delete a few of the redundant members or a few of the members which are not supposed to be there in the model. I have selected the base members. Basically, it's a factory shed where it's supposed to rest on the columns. So I am just deleting the lowermost members. So we have cleaned the members which are at the support level. We don't need them. Now next, assign all the bottommost nodes, which are the support nodes, and then assign them with the required support. For example, here I am taking as a fixed support. You can also assign as a pin support. So I have selected the support nodes and assign the fixed support.